Based on evidence, scientists have learned that our universe began over 13.7 billion years ago. The moment it all began is called the Big Bang. In this part of our unit, we will learn about the evidence that has been found that supports this claim. We will look at each of these types of evidence that support the Big Bang theory with the upcoming slides. Henrietta Leavitt discovered that stars known as Cepheid variables change in brightness with a period that is related to their distance. By measuring the period of their brightness change, astronomers now had a method to calculate their distance from Earth. Vesto Slipher used a method known as redshift to find the speed of a galaxy's motion. Hubble found that when you compared the distance to a galaxy to the redshift of its light, the farther away it was the faster it was moving away from us. This distance-speed relationship is now known as Hubble's law. All types of waves are affected by the motion of the object that produces them. With cars, the Doppler effect causes the sound to be pitched higher as a car approaches you. The sound waves are being compressed. When the car passes you by, the sound waves are stretched, lowering the pitch of the sound. The same thing happens with light waves. Galaxies that are moving away from us have their light stretched toward the long wave end of the spectrum, which is red. So this is why we say that a galaxy's light is red-shifted. The laboratory reference provides a view of the spectrum of a gas at rest, from our frame of reference. Explain how the distance to other objects, specifically the galaxies, increases as the redshift increases. Stop here and do the Hubble's law graphing investigation. When Hubble plotted the distances to galaxies versus their speed, he found a direct relationship: the farther away a galaxy was, the faster it was moving. The only atoms that formed directly from the Big Bang were hydrogen and helium. The amount of hydrogen formed was much greater than the amount of helium. Stars turn hydrogen into helium as they produce energy in their cores by nuclear fusion. So, the amount of hydrogen compared to helium changes as time passes. Estimating the ratio of hydrogen to helium after the Big Bang, knowing how fast stars process it into helium, and measuring the ratio of these elements to each other today allows us to estimate the age of the universe. The Big Bang theory predicts that a huge release of energy was released at the moment our universe began. At that moment, it was a very high energy, short-wave radiation, as the young universe was incredibly hot. Because the universe is expanding, the wavelength of the radiation stretched to longer wavelengths due to the Doppler effect. By today, the theory predicted the radiation left over from the Big Bang should be in the microwave portion of the electromagnetic spectrum. Its signal was found by two scientists working to track down an unknown interference on early satellite communication systems. The image shows Penzias and Wilson standing in front of the antenna used to discover the cosmic background radiation. Penzias and Wilson knew they had found the cosmic background radiation because the signal was the same no matter where they pointed their antenna. The signal was coming from everywhere in space. The CHHS satellite made a detailed map of the CBR, showing areas of higher and lower temperature in the early universe. These reflected areas of higher and lower density, showing that matter was gathering into the structures we see today: galaxies, clusters, superclusters, voids. The Wilkinson Microwave Anisotropy Probe was a follow-up mission to CHHS, and provided a much higher resolution map of the distribution of matter in the early universe. It shows the locations of concentrations of matter, as well as voids, in much greater detail. It took 7 years of data collection to make this map. The reddest regions contain the most matter. These areas of greater density were the seeds of galaxy formation. When astronomers observe the motions of galaxies, they see something not easily explained. There doesn't seem to be enough matter in galaxies to explain the ways they move. There must be something affecting their motion that astronomers can't detect. They are calling these unknown influences dark matter. Some astronomers think that dark matter may consist of countless small, dark objects called brown dwarfs. So far, no definitive discoveries of these objects have been made. Measurements of the redshift of distant Type Ia supernovae have yielded a surprising result: the expansion of our universe is speeding up. Scientists are building devices in an attempt to prove the existence of weakly interacting massive particles. These two are yet to be proven to exist. Why is understanding the structure and expansion rate of our universe important? In practical terms, it isn't. But we are a curious people. It would be nice to know the eventual fate of the universe. Will it continue to expand forever, or will it slow and start to collapse? Either of these things will occur in the far distant future.